Hello there, and welcome. My name is Matthew Gray, and I'm grateful you've chosen to be here tonight. Right now, wherever you find yourself in this world, let this be your invitation to pause. Tonight, we're not venturing into distant galaxies or imagining faraway worlds. We're staying right here on Earth. And what we'll discover together is that this planet, the one beneath your feet, is far more astonishing than most of us ever stop to realize. From the deep oceans that pulse with light to the ancient forests that breathe in ways we're only beginning to understand. From the mountains that hold stories written in stone to the smallest creatures that carry the secrets of survival. Our world is alive in ways that will surprise you, comfort you, and maybe even change the way you see tomorrow morning's sunrise. There's a harmony here, a balance so precise, so quietly magnificent, that it borders on the miraculous. The way our moon pulls the tides, the way the atmosphere shields us, while letting in just enough light to grow the food we eat. The way the Amazon rainforest breathes oxygen into the air, while ancient underground networks connect trees like a vast, living conversation. We are part of a single, breathing system, and tonight you'll hear how beautifully it all fits together. Some of what you hear might gently shift your perspective. Other moments will simply drift by like clouds across a summer sky, soft and unhurried, and quietly unforgettable. If this brings you peace, if it sparks something curious and warm inside you, I'd be honored if you liked and subscribed. It helps others find this place too, one restless mind at a time. For now, settle in. The air you're breathing right now has been breathed before, not by someone you know, necessarily, though that's possible too. Every breath you take contains roughly 25 sextillion molecules. The atmosphere doesn't forget. When you breathe in, you're not just taking in oxygen, you're participating in a process unfolding for billions of years. There's something quietly profound about this, and it's not just historical figures. Every person you've ever stood near, every stranger you passed on a crowded street, has shared molecules with you. This exchange doesn't stop with humans, and our atmosphere is astonishingly thin. So, as you lie here tonight, breathing in and out, know that you are part of something larger, something ancient and ongoing. That connection between breath and time, between your lungs and history itself, leads us to consider another kind of connection happening beneath the surface of our seas. The ocean, covering more than 70% of our planet's surface, is not silent. Whales sing to each other across distances that seem impossible. A humpback's song, low and mournful and oddly melodic, can travel for thousands of miles underwater. These songs are not random, but whales are not the only ones making noise. Even the ocean floor contributes. Underwater earthquakes rumble. And yet, to us, standing on the shore, it often seems quiet. There's a reason for that. The sound of waves follows a pattern mimicking the rhythm of breathing. But beneath that surface calm, there is an entire world of sound happening just out of earshot. And in a way, that's comforting. So, when you hear the sound of waves, whether in person or in your memory, let it remind you of that hidden music. Let it carry you gently toward rest, knowing that somewhere, deep in the dark water, life is singing its quiet songs. And just as sound travels through water in ways we can't always perceive, there are connections happening beneath our feet that we rarely consider. Trees talk to each other. Beneath the ground, hidden from view, there is a vast network of fungal threads called mycelium. These threads connect tree roots to each other, forming what scientists call the wood wide web. If one is attacked by insects, it can send chemical signals through the mycelium to nearby neighbors, warning them of the danger. Older trees, often called mother trees, play a special role in this network. Even more surprising, trees can recognize their own offspring. A mother tree will send more nutrients to its own seedlings than to unrelated individuals. This changes the way we think about forests, and it's not just trees and fungi. The mycelial network also connects to bacteria, to insects, to the entire ecosystem. There's something deeply reassuring about this. The next time you walk through a forest, remember that you are walking over a hidden world. And maybe, in some small way, this can change how we see the world. Not as a place of endless struggle, but as a place where life, in all its forms, has learned to help each other. This quiet cooperation extending below ground finds its echo in the very foundation of our planet itself. Our planet hums. This hum is different from the vibrations caused by earthquakes or volcanic activity. It's always present, even on the calmest days, even when the ground feels perfectly still. The source is still debated. What's remarkable is that this hum is global, and in a poetic sense, that's exactly what's happening. Our planet is not a dead rock floating through space. We don't notice this hum in our daily lives. There's something oddly comforting about this. It means that even when everything feels still, even in the quietest moments, our world is never truly at rest. Some researchers have even suggested this hum might have subtle effects on living things. It's hard to say for certain. So tonight, as you lie still, imagine that hum. Imagine our world beneath you, vibrating gently, endlessly, a quiet presence here, long before you, and continuing long after. And just as this vibration is imperceptible yet constant, there are other subtle signals in our world that we sense without quite knowing why. Rain smells the way it does because of a molecule called geosmin. Geosmin is produced by soil-dwelling bacteria called actinomycetes. These bacteria are everywhere, breaking down organic matter in the soil, playing a quiet but essential role in the decomposition process, returning nutrients to the ground. Humans are extraordinarily sensitive to geosmin, but there's a reason for this sensitivity. Even today, in a world where most of us don't rely on rain for immediate survival, that ancient association remains. The smell still triggers something deep in our brains. And it's not just geosmin. There's also ozone, forming when lightning splits oxygen molecules in the atmosphere. Ozone has a sharp, clean scent, almost metallic, and it often arrives before the rain itself. Together, these scents create the experience of rain, and maybe that's why we find it so calming. This renewal, this sense of cycles continuing, extends even to the celestial companion that's been with us since the beginning. The moon is slowly drifting away from us, not quickly. Billions of years ago, when our world was young, the moon was much closer. This is not a cause for concern. Our lunar companion is not going to leave us. Its presence has shaped life here in profound ways. Without our companion, this world would be very different. And there's something poetic about the fact it's moving away. It suggests even the most enduring relationships change over time. For now, though, it's close enough. So, the next time you see the moon, think about that slow drift. Think about the billions of years it has been circling our world, the countless nights it has illuminated, the tides it has pulled, the lives it has touched. And while the moon moves through the darkness above, there are creatures below, creating their own light in the deepest reaches of the sea. Deep in the ocean, there are places where light never reaches. One of the most surprising things about the deep ocean is that much of it glows. They do this using chemical reactions within their bodies. Special cells called photophores contain a molecule called luciferin, which, when combined with oxygen and an enzyme called luciferase, produces light. Some creatures use bioluminescence to attract prey. Still others use bioluminescence to communicate. Certain species of squid flash patterns of light to signal to each other, coordinating hunts or attracting mates. And then there are creatures producing light simply because they can. This bioluminescence has a strange beauty to it. The deep sea is also home to some of the strangest creatures on our planet. There are fish with transparent heads, allowing them to see upward through their own skulls. And the vast majority of the deep ocean remains unexplored. But what we do know is enough to inspire a quiet sense of wonder. The deep ocean, dark and cold and seemingly inhospitable, is not a dead zone. So, when you think of the ocean, don't just picture the sunlit surface, the waves and the beaches. And as these creatures create light in the darkness, there's another form of light floating above us that carries more weight than it appears. Clouds are heavier than they look. This seems impossible at first. Clouds look weightless. The reason clouds don't fall is because the water droplets making them up are tiny. But those droplets add up. A typical cumulus cloud might contain several 100,000 tons of water, all spread out over a large volume. Eventually, of course, the droplets do fall. But before that happens, before the droplets grow heavy enough to fall, they float. Clouds also play an important role in regulating temperature. They reflect sunlight back into space, helping to keep the planet cool. Different types have different effects. What's clear is that clouds are far more important than they might seem. They're not just decorations in the sky, not just something to watch on a lazy afternoon. And they're beautiful. So, the next time you see a cloud, remember it's heavier than it looks. This ability to preserve and endure, despite appearing delicate, is something we see in unexpected places on our world. Honey never spoils. Archaeologists have found pots of honey in ancient Egyptian tombs, sealed away for thousands of years. And when they opened them, the honey was still perfectly edible. There are a few reasons for this remarkable longevity. Second, honey is acidic. It has a pH level between 3 and 4.5, low enough to kill most microorganisms. Third, honey contains hydrogen peroxide. All of these factors combine to make honey one of the most stable foods in existence. This is part of why honey has been so valued throughout history. It's not just a sweetener, and bees, of course, make it all possible. There's something almost miraculous about the fact such a simple substance, made by such small creatures, can last so long. That honey, produced by bees following instincts honed over evolutionary time, can outlive civilizations. It's a reminder that nature, when left to do what it does best, creates things that endure. So, when you taste honey, think about that. Just as honey is preserved by its own properties, our world itself is protected by forces we cannot see. Our magnetic field is invisible, but it's one of the most important things protecting life on this planet. Without it, the solar wind, a constant stream of charged particles from the sun, would strip away our atmosphere, leaving the surface exposed to deadly radiation. The field is generated deep within the planet, in the outer core, where molten iron flows and churns. The field isn't static, it shifts and changes over time. Even more dramatic, the field has reversed completely in the past. During a reversal, the field weakens, becoming chaotic and unstable. But for now, the field is stable. It stretches out into space, forming a region called the magnetosphere, which deflects the solar wind and traps charged particles in bands called the Van Allen belts. The field also creates one of the most beautiful natural phenomena, the aurora. People have been watching the aurora for thousands of years, inventing myths and stories to explain the lights. Some cultures believed they were the spirits of the dead. Others thought they were omens, messages from the gods. And the field does more than protect us. So, even though we can't see it, can't feel it, the field is there, quietly doing its job, shielding us, guiding life, creating beauty in the night sky. Just as this invisible shield protects us, there are visible giants on our world that have stood through countless ages. Mountains are not permanent. They rise, they erode, they eventually wear down to nothing. The Himalayas, the tallest mountain range on our planet, are still growing, but even as the Himalayas grow, they're also being worn down. Glaciers grind against the rock, carving deep valleys. The Appalachian Mountains, for example, are ancient, and yet, even in their diminished state, the Appalachians have a quiet beauty. Mountains also create their own weather. When moist air is forced to rise over a mountain range, it cools, and the water vapor condenses, forming clouds and rain. This effect shapes entire ecosystems. And then there's the simple fact: mountains are places of refuge. For plants and animals that can't tolerate heat, they offer cooler climates, even in the tropics. But they are also fragile. For now, though, mountains stand. These cycles of creation and erosion play out not just on land, but in the vast darkness surrounding our world. The stars you see at night are not where they appear to be. Light takes time to travel, and the distances involved are so vast, the light reaching your eyes left those stars years ago. This means when you look at the night sky, you're looking back in time. More distant stars are even more delayed. Some visible to the naked eye are hundreds of light years away. This creates a strange sense of dislocation. And yet, despite these vast distances, despite the fact the light has traveled so far, it still reaches us. The light from the sun, by contrast, is much more recent. It takes just over 8 minutes for sunlight to reach our world. But even that 8-minute delay has implications. This idea, that light takes time to travel, seems simple. But it fundamentally changed how we understand the universe. It also means the universe is much larger than it appears. And so the night sky, which seems so simple, so straightforward, is actually layered with complexity. Just as stars illuminate the night, there are humbler things on our world that tell their own stories. Sand is not just one thing, it's a collection of tiny fragments, each one a piece of something larger, broken down over time by wind and water and the slow grind of geological processes. In Hawaii, many beaches are black, made of tiny fragments of volcanic rock, basalt, shattered and ground down by the waves. Every grain tells a story. It's a piece of a rock, once part of a mountain, or a fragment of a shell, once part of a living creature. The process of creating sand is slow, and once sand is created, it doesn't stay in one place. There's something oddly soothing about this. Sand, which seems so static when you're lying on a beach, is actually flowing, shifting, part of a process spanning continents and millennia. And sand is not just on beaches. But on our world, sand plays another important role. It's a habitat. Sand is also a resource. But for now, there's still plenty. And just as sand has been carried by water for millions of years, there are waterways carving paths through stone with the same patient persistence. Rivers are older than the mountains they cut through. This seems impossible at first. When a mountain range begins to rise, rivers are already flowing across the landscape. This creates something called an antecedent river, one that predates the mountains it flows through. The Grand Canyon is a perfect example. The canyon walls reveal layers of rock, each one representing a different period in history. Rivers shape the land in other ways too, but rivers are not just agents of erosion, they're also lifelines. And rivers are constantly changing. There's something deeply calming about rivers. The sound of flowing water is almost universally soothing, and they connect things. So, when you see a river, think about its age. And beneath the rivers, beneath the waves, there are movements of water we rarely consider. The ocean is full of waves, but not all of them are on the surface. Deep below, in the dark, there are internal waves, massive movements of water we can't see from above. Internal waves can be enormous. These waves are created by the same forces creating surface waves: wind, tides, and the interaction between water and obstacles like underwater ridges or continental shelves. When tidal, currents flow over a ridge. They can generate internal waves propagating outward, traveling for hundreds of miles before dissipating. Internal waves affect the ocean in important ways. And internal waves don't just stay deep. The existence of internal waves is a reminder the ocean is not uniform. It's layered, stratified, with boundaries and gradients we don't see, but that have real effects. And that system is constantly moving. This circulation is called thermohaline circulation, and it's driven by the fact cold, salty water is denser than warm, fresh water. When surface water near the poles cools, it becomes denser and sinks, starting a slow journey along the ocean floor toward the equator. This process takes centuries, so the ocean, which seems so simple from the shore, is actually full of hidden complexity. But even without understanding every detail, we can appreciate the beauty of it. Waters are vast, mysterious, full of life and movement. And while water moves below in ways we can't see, above the surface, another form of water falls in ways uniquely beautiful. Snow is not just frozen rain. Each snowflake starts as a tiny ice crystal, forming around a nucleus, which could be a speck of dust, a pollen grain, or even a bit of sea salt, carried up by the wind. As the crystal falls through the atmosphere, it encounters different conditions, different temperatures, different levels of humidity. The result is that no two snowflakes are exactly alike. Snowflakes have a six-sided symmetry, a consequence of the molecular structure of ice. The shape tells you something about the conditions it formed in. Thin, flat plates form in relatively warm air, just below freezing. When snowflakes fall, they accumulate, layer upon layer, creating a blanket insulating the ground. Snow also reflects light, which is why a snow-covered landscape looks so bright, even on overcast days. About 80 to 90% of sunlight hitting fresh snow is reflected back into the atmosphere. But snow doesn't last forever. This slow release is important. There's also something undeniably peaceful about snow. It muffles sound, absorbing noise, creating a quiet feeling almost magical. And snow is fragile. So snow is more than just frozen water. It's a substance with its own unique properties, its own beauty, its own role in the systems of our world. And just as each snowflake is unique, each living thing on our planet has its own remarkable story of survival. Trees are some of the oldest living things on our world. The oldest known tree species still alive today is the ginkgo. Individual trees can also live for astonishingly long times. Bristlecone pines, found in the mountains of the western United States, are among the longest-lived organisms on the planet. These trees grow slowly, adding just a tiny ring of wood each year, sometimes less than a millimeter. Other trees live long lives in different ways. Some, like aspens, reproduce by sending up shoots from their roots, creating groves that are all genetically identical, all connected underground. Trees also have a remarkable ability to survive damage, and trees change the environment around them. Forests, in turn, influence weather patterns on a larger scale. The Amazon rainforest, for example, generates much of its own rainfall, but forests are fragile in their own way. For now, though, there are still forests, still places where trees stand tall, where the air is cool and green, where sunlight filters through the canopy in shafts of gold. And they'll keep growing as long as we let them. And beneath the forests, beneath the soil they've enriched over millennia, there are depths we've barely explored. The deepest hole ever drilled is only about 7.5 miles deep. That hole is the Kola Super Deep borehole, located in Russia, drilled during the Soviet era as part of a scientific project to learn more about the crust. Drilling started in 1970 and continued for over 20 years. The project was eventually abandoned, but it provided valuable information about the composition of the crust, about the types of rock found at different depths, about the way heat flows through the ground. But even with all that effort, they barely scratched the surface. The crust is the thinnest layer, ranging from about 3 miles thick under the oceans to about 25 miles thick under the continents. We've never directly sampled the mantle. The core is even more remote. The inner core is about 750 miles in radius, a solid sphere of iron and nickel under unimaginable pressure, heated to temperatures comparable to the surface of the sun. It's spinning, though not quite at the same rate as the rest of the planet, creating the magnetic field protecting us from solar radiation. All of this happens deep below our feet, completely out of sight, completely beyond our reach. It's humbling in a way. We've explored the surface extensively, but that doesn't stop us from learning. So this planet, which seems so solid, so familiar, is actually full of mysteries. And among the most mysterious processes are those that shaped the landscapes we see today. Glaciers are rivers of ice, but they move so slowly you'd never notice it by watching. Most creep forward at a rate of just a few inches per day, though some move faster, especially during warmer months when meltwater lubricates the bottom, allowing the ice to slide more easily over the bedrock. But even at that slow pace, glaciers are incredibly powerful. The valleys carved by glaciers are U-shaped, with steep sides and flat bottoms, unlike the V-shaped valleys created by rivers. This is because glaciers erode the entire width of the valley floor, not just a narrow channel. Glaciers also create other features: moraines, which are piles of rock and sediment pushed to the sides or front; drumlins, which are streamlined hills formed by the flow of ice over sediment; and eskers, which are long, winding ridges of sand and gravel deposited by meltwater streams flowing beneath the ice. During the last ice age, which ended about 11,700 years ago, glaciers covered much of North America, Europe, and Asia. And glaciers are still at work today, though most are retreating, shrinking as the climate warms. But glaciers do more than just shape the land. They store water, acting as natural reservoirs, releasing it slowly over time. Glaciers also preserve history. In a way, glaciers are time machines. They hold records of the past, locked in ice, waiting to be read. But glaciers are also vulnerable. This is not a distant, abstract problem. But for now, there are still glaciers. Still places where ice stretches to the horizon, blue and white and ancient. And in stark contrast to these frozen giants, there are places where water is so scarce it defines entire landscapes. Deserts are not always hot. The Atacama Desert in Chile is another example. It's one of the driest places on the planet, with some weather stations never having recorded a single drop of rain. Deserts exist because of the way air circulates in the atmosphere. But deserts are not lifeless. Deserts also change. They expand and contract over time, responding to shifts in climate. And deserts can be beautiful. There's a simplicity to deserts, a starkness some people find appealing. Life here is stripped down to essentials. Deserts also hold secrets, and they remind us this world is diverse. So deserts, despite their reputation, are not empty. They're full of life, full of history, full of beauty. And above these harsh landscapes, above all the varied terrain of our world, there's a layer of protection we rarely think about. Our atmosphere is divided into layers, each with its own characteristics. Above the troposphere is the stratosphere, extending up to about 30 miles. This is where the ozone layer is, a region of higher ozone concentration, absorbing most of the sun's harmful ultraviolet radiation. Above the stratosphere is the mesosphere, extending to about 50 miles. Higher still is the thermosphere, where the air is incredibly thin and temperatures can soar to over 3,000 degrees Fahrenheit. Though the air is so sparse, it wouldn't feel hot in the traditional sense. And finally, there's the exosphere, the outermost layer, where the atmosphere gradually fades into space. There's no clear boundary, no sharp line where it ends. Each layer plays a role in protecting our world, in regulating temperature, in shaping the weather. And the atmosphere is not static. It's constantly in motion, driven by the uneven heating of the surface. These patterns are predictable, but they're also influenced by countless factors. The rotation of the planet, the distribution of land and ocean, the height of mountains, the presence of ice. The atmosphere also interacts with the ocean. All of this happens invisibly, constantly, without us noticing. We walk around under a blanket of air, taking it for granted, barely aware of the processes keeping it stable, keeping it breathable, keeping it protecting us from the harshness of space. But the atmosphere is not invulnerable. And yet, for now, the atmosphere still does its job. It still shields us from radiation, still distributes heat, still carries moisture from the oceans to the land. And in the waters below this protective layer, there are ecosystems of stunning beauty and complexity. Coral reefs are sometimes called the rainforests of the sea, and the comparison is apt. Corals themselves are animals, not plants, though they often look like colourful rocks or plants swaying in the current. But corals don't live alone. They have a symbiotic relationship with microscopic algae called zooxanthellae, living inside the coral's tissues. This relationship is why corals are so colourful. Coral bleaching has become more common in recent years as ocean temperatures have risen. Large sections of reefs around the world have bleached, and many have not recovered. But reefs are resilient, at least to a point. Reefs also face other threats. Despite all of this, there are still healthy reefs, places where the water is clear, where fish swim in schools so dense they block out the light, where the coral grows thick and vibrant. Reefs also protect coastlines, and reefs have value beyond their ecological role. They support fisheries, providing food and income for millions of people. So reefs matter. For now, there are still reefs. And just as electricity flows through coral reefs in the form of life, there's another form of electrical discharge illuminating our skies. Lightning is a discharge of static electricity, the same basic phenomenon making your hair stand up when you rub a balloon on it, but on a vastly larger scale. Inside a thunderstorm, ice particles collide, transferring charge. When the field becomes strong enough, it overcomes the resistance of the air, and a bolt of lightning leaps between the cloud and the ground, or between different parts of the cloud. Lightning happens more often than most people realize. At any given moment, there are about 2,000 thunderstorms active around the world, and lightning strikes our planet about 100 times every second. Some places are struck more often than others. Lightning is not just a curiosity. Lightning can also start fires, particularly in dry climates where vegetation is ready to burn. Some ecosystems, like certain pine forests, have evolved to depend on fire. Of course, lightning is dangerous. But despite the danger, or perhaps because of it, lightning has always fascinated people. It's sudden, dramatic, powerful, a reminder the atmosphere contains enormous amounts of energy waiting to be released. And lightning is beautiful. So lightning, for all its danger, is also a reminder of the vitality of our world. And high above, untouched by storms, there's a companion that bears the marks of a very different kind of history. The moon has no atmosphere, which means there's no wind, no weather, no erosion of the kind we see here. Footprints left by the Apollo astronauts in 1969 are still there, unchanged, and will remain for millions of years, unless disturbed by a micrometeorite impact or future human activity. This lack of atmosphere also means the surface experiences extreme temperature swings. The surface is covered in a layer of fine dust called regolith, created by billions of years of micrometeorite impacts. These tiny impacts, too small to leave visible craters, gradually pulverize the rock, creating a layer of dust several feet thick in some places. But the moon is not entirely dead. The surface also holds a record of the solar system's history. The largest of these is the South Pole Aitken Basin, a crater over 1,500 miles in diameter and more than 5 miles deep. It's one of the largest impact craters in the solar system, formed by a collision so violent it probably excavated material from the mantle. The moon also experiences moonquakes, though they're much weaker than earthquakes. The far side, the side we never see from here, is different from the near side. It has more craters, fewer maria, which are the dark, flat plains we see as the man in the moon, and thicker crust. And the moon is still changing, though slowly. The moon has been humanity's companion for as long as there have been humans. But even with all we've learned, the moon still holds mysteries. Questions about how it formed, about its interior, about the water ice at the poles, about what future exploration might uncover. And beneath our feet, beneath the surface of our own world, there's a layer supporting everything that grows. Soil is not just dirt. Soil forms slowly, over thousands of years, as rock breaks down and mixes with organic matter. From decaying plants and animals, the process is gradual, patient, and essential. Different types have different characteristics. Soil also has layers, called horizons. These layers took time to form. In some places, it can take 100 years or more to create just 1 inch of topsoil. Erosion is a natural process, but it's accelerated by human activity. But soil is also resilient, at least when given a chance. Cover crops, planted between main growing seasons, protect the soil from erosion, add organic matter, and improve soil health. These practices, and others like them, work with the soil rather than against it. Recognizing soil is a resource needing to be managed carefully, protected, nurtured. The organisms in soil play important roles. Fungi form networks in the soil, similar to the mycelium connecting trees in a forest. These networks help plants absorb water and nutrients, and in return, the plants provide the fungi with sugars from photosynthesis. Bacteria break down organic matter even further, releasing nitrogen, phosphorus, and other elements plants need. All of this activity happens out of sight, beneath the surface, in the dark and damp spaces between soil particles. But it's essential, so soil is more than just dirt. And just as soil is alive with unseen activity, there are forces beneath the crust that periodically make themselves dramatically known. Volcanoes are openings in the crust where molten rock, ash, and gases escape from below. There are about 1,500 active volcanoes on land, and many more under the ocean. An active volcano is one having erupted recently, or showing signs of potential activity. Volcanic eruptions vary widely in intensity. The type of eruption depends on the viscosity of the magma. Runny, low-viscosity magma, like the kind found in Hawaii, allows gases to escape easily, resulting in relatively gentle eruptions. Volcanic eruptions can have global effects, but volcanoes also create. Volcanic soil is incredibly fertile. The ash and lava weather quickly, releasing nutrients plants need. Volcanoes also provide geothermal energy, and volcanoes remind us our planet is not a static place. The crust is thin, the mantle below is hot and moving, and the pressure and heat are constantly seeking release. There's something awe-inspiring about volcanoes. For people living near volcanoes, they're part of life. But predicting eruptions is not an exact science. Volcanoes are complex, and each one behaves differently. So volcanoes are dangerous, but they're also fascinating. And just as volcanoes connect the interior to the surface, there are other forces connecting the oceans to the land. Tides are the rise and fall of sea levels, caused primarily by the gravitational pull of the moon, and to a lesser extent, the sun. As our world rotates, different parts of the planet pass through the regions where the moon's gravity pulls the water upward, creating high tides. Most coastlines experience 2 high tides and 2 low tides each day, roughly 6 hours apart, though the exact timing varies depending on the shape of the coastline and the depth of the ocean floor. The Bay of Fundy has the highest tides in the world, the result of the bay's shape and depth, which create a resonance amplifying the tidal effect. Tides also affect rivers, pushing salt water upstream during high tide, then allowing fresh water to flow back downstream during low tide. This mixing creates estuaries, brackish environments where salt and fresh water meet, supporting unique ecosystems, serving as nurseries for many marine species. The timing of the tides is predictable, calculated based on the positions of the moon and sun, but the exact height can be influenced by weather. The sun also affects tides, though its influence is weaker than the moon's because it's so much farther away. When the sun, moon, and our world align during a new moon or full moon, their gravitational pulls combine, creating higher than usual high tides and lower than usual low tides, called spring tides. Tides have been important to humans for thousands of years, but tides are not just useful, and tides connect us to the past. Ancient peoples watched the same tides, relied on them, built their lives around them. The moon, pulling the tides, has been doing this work for billions of years. And preserved within the rocks shaped by these ancient tides are glimpses of life from eons past. Fossils are the preserved remains of ancient life, trapped in rock, offering us glimpses into worlds no longer existing. Most organisms don't become fossils. This process is rare. The fossil record is incomplete, biased toward organisms with hard parts, like bones or shells, more likely to survive the fossilization process. But despite these limitations, fossils have told us an enormous amount. They've shown us that life has existed on our planet for over 3.5 billion years, starting with simple, single-celled organisms and gradually becoming more complex. The most famous of these extinctions happened 66 million years ago, when an asteroid struck our world, ending the age of the dinosaurs. But fossils show more than just extinction. They show evolution, the gradual change of species over time. Fossils of early whales, for example, show a progression from land-dwelling mammals to fully aquatic creatures. And fossils are still being discovered. So, fossils are more than just old bones. They're messages from the past, written in stone, waiting to be read. And just as fossils preserve the past in stone, there are places on our world where other kinds of preservation happen in unexpected ways. Caves form slowly, carved from rock by the patient work of water. The result is a hidden world beneath the surface, with passages and chambers, underground rivers and lakes, formations that seem almost otherworldly. Stalactites hang from the ceiling, formed by water, dripping down and depositing minerals. These formations grow at a rate measured in inches per 1,000 years. Caves are also remarkably stable environments. Some cave-dwelling creatures have lost features they no longer need. Fish living in cave streams often have no eyes, no pigmentation, their bodies pale and translucent. Bats also use caves, roosting in large colonies during the day and emerging at dusk to hunt. Caves have been used by humans for thousands of years, as shelters, as ceremonial sites, as sources of water. Exploring caves requires care, and caves are still forming, so caves are windows into a hidden world, a reminder that our planet is not just what we see on the surface. Beneath our feet, there are spaces we rarely think about, ecosystems we rarely encounter, processes going on for longer than we can easily comprehend. And just as caves form drop by drop over millennia, there are other phenomena shaped by water falling from above. Clouds are made of tiny water droplets or ice crystals, so small and light that they float in the air. As the vapor rises, it cools. Cool air can't hold as much moisture as warm air, so when the temperature drops below a certain point, called the dew point, the vapor begins to condense, forming tiny droplets around particles of dust or pollen or salt. Inside the cloud, the droplets collide and merge, growing larger. The size of raindrops varies, but most are between 1 and 5 millimeters in diameter. Rain is essential. It replenishes rivers and lakes, soaks into the ground to recharge aquifers, waters crops and forests. But rain is not evenly distributed. Rain also varies in intensity. A light drizzle might deposit less than 1/10 of an inch per hour, and rain affects mood. Rain also cleans the air. So rain is more than just water falling from the sky. It's a process, a cycle, a connection between the ocean and the land, between the atmosphere and our world. The Amazon rainforest produces about 20% of the world's oxygen, though this is often misunderstood. But the Amazon is still important. It stores vast amounts of carbon, about 150 billion tons, locked up in the trees and soil. The forest also influences weather patterns, both locally and globally. The Amazon is home to an astonishing diversity of life, but the Amazon is fragile. Deforestation, driven by logging, agriculture, and development, has removed about 20% of the forest, and the rate of loss continues. This would be a loss not just for the Amazon, but for the entire planet. But there's also hope. Efforts to protect the Amazon, to slow deforestation, to restore damaged areas are ongoing, and the Amazon continues to inspire. Walking through the Amazon is an experience unlike any other, and the Amazon reminds us that our planet is full of places we don't fully understand. Systems we're only beginning to appreciate. Connections we're just starting to recognize. It's a living library, holding knowledge in its trees, its soil, its creatures. Knowledge that could be lost if we're not careful. So, the Amazon matters. And just as the Amazon is a vast reservoir of life on land, there are frozen reservoirs drifting through the seas. Icebergs are massive chunks of ice having broken off from glaciers or ice shelves, floating in the ocean, slowly melting as they drift toward warmer waters. The ice is fresh water, frozen from snow that fell centuries or even millennia ago, compacted over time into dense, crystalline ice. Only about 10% of an iceberg is visible above the water. Icebergs come in many shapes and sizes. As icebergs melt, they sometimes make noise. The ice cracks and groans, releasing air bubbles trapped for thousands of years. Icebergs also carry sediment, rocks and soil picked up by the glacier as it moved across the land. And icebergs affect the ocean. As they melt, they release fresh water, which is less dense than salt water, creating layers in the ocean that can influence currents. In recent years, more icebergs have been breaking off from glaciers, a sign of warming temperatures. But icebergs have always been part of the polar regions. There's something haunting about icebergs. They're beautiful, glowing white and blue in the polar sun, sculpted by wind and waves into fantastic shapes. So icebergs are more than just floating ice. And while some ice floats on the surface, there are grains of sand on beaches that hold their own magnetic secrets. The sand on some beaches is magnetic. You can test this yourself with a magnet, dragging it through the sand and watching as dark grains cling to it. Magnetite forms in igneous rocks, crystallizing from molten magma as it cools. The magnetic properties of magnetite have been known for thousands of years. Magnetite is also found in living organisms. Some bacteria use tiny crystals of magnetite to orient themselves in the magnetic field, swimming along magnetic field lines to find the conditions they prefer. humans have even been found to have trace amounts of magnetite in their brains, though its function, if any, is still unclear. On a larger scale, magnetite is an important ore of iron. It's mined in large quantities, processed, and used to make steel. But on the beach, magnetite is just another grain of sand, mixed in with quartz and shell fragments, worn smooth by the waves. There's something satisfying about this. And just as magnetite responds to invisible forces, there are waterways responding to gravity in ways that seem to defy their surroundings. Rivers flow downhill, pulled by gravity, always seeking the lowest point. But they don't flow in straight lines. This meandering happens because water doesn't flow evenly. Eventually, the loops can become so extreme, the river cuts through the narrow neck of land between two bends, shortening its course and leaving behind an oxbow lake, a crescent-shaped body of water, longer part of the main river. These lakes gradually fill with sediment, turning into wetlands, then dry land, but they remain visible features of the landscape, scars left by the river's former path. Rivers are constantly changing, but floods are also natural, even necessary. Rivers also connect ecosystems. Fish migrate upstream to spawn, carrying nutrients from the ocean into freshwater environments. And rivers are culturally significant, but rivers are also vulnerable. Pollution, dams, water extraction, all affect the health of rivers, altering their flow, degrading water quality, disrupting the ecosystems depending on them. Protecting rivers means understanding they're not just channels for water. And just as rivers connect land to sea, there are organisms connecting different parts of ecosystems in ways we rarely see. Mushrooms are not plants. The mushroom itself is just the fruiting body, the part of the fungus producing spores. The main body, called the mycelium, is a network of thread-like structures spreading through the soil or wood, often over large areas. Fungi are essential decomposers. Some fungi form partnerships with plants, creating mycorrhizal associations, where the fungal mycelium connects to plant roots. The fungus helps the plant absorb water and nutrients, especially phosphorus, which is often scarce in soil. Other fungi are parasitic, infecting plants or animals, causing disease. But fungi are also used by humans. And some mushrooms are edible, prized for their flavor and texture. Others are deadly poisonous, containing toxins that can cause liver failure, hallucinations, or death. Mushrooms also appear suddenly, seemingly overnight. There's something almost magical about mushrooms. They emerge from the earth, exist for a few days, release their spores, and then wither away, leaving barely a trace. And just as fungi work invisibly beneath the ground, there are structures beneath the ocean that are among the largest living things on our planet. The Great Barrier Reef, off the coast of Australia, is the largest living structure on our world. Coral reefs grow slowly, just a few centimeters per year. The reef is home to an extraordinary diversity of life. Over 1,500 species of fish, 400 species of coral, 4,000 species of mollusks, and countless other organisms live there, from sea turtles and dolphins to sharks and rays. But the Great Barrier Reef is under threat. The loss of the Great Barrier Reef would be a tragedy, not just for Australia, but for the world. It's a natural wonder, a place of stunning beauty, a source of livelihood for thousands of people, and a habitat for countless species. But for now, the reef endures, and the reef remains a place of wonder. And while the reef pulses with life beneath the waves, there are lights dancing above, that speak to entirely different forces. Auroras, those shimmering curtains of light dancing across the sky near the poles, are caused by interactions between the solar wind and the magnetic field. The solar wind, a stream of charged particles from the sun, flows constantly through space, and when it encounters our world, most of it is deflected by the magnetic field. But near the poles, where the magnetic field lines converge, some particles can penetrate into the atmosphere. Auroras are most common during periods of high solar activity, when the sun releases bursts of particles called coronal mass ejections. These ejections can enhance the aurora, making it brighter, more widespread, visible at lower latitudes than usual. The aurora borealis, or northern lights, is the aurora seen in the northern hemisphere. People have been watching auroras for thousands of years, creating myths and legends to explain them. Watching an aurora is a humbling experience. The lights move in ways seeming deliberate, almost intelligent, shifting and swirling, brightening and fading. Auroras also occur on other planets. So, auroras are a reminder that our planet is not isolated. We're constantly being bathed in particles from the sun, constantly interacting with the solar wind, constantly protected by our magnetic field. And just as the aurora reveals invisible forces, there are sudden releases of energy within our world that reshape landscapes in moments. Earthquakes are sudden releases of energy in the crust, caused by the movement of tectonic plates. Eventually, the stress becomes too great, and the plates slip, releasing the accumulated energy in a matter of seconds. Most earthquakes are small, barely noticeable. Our planet experiences millions of earthquakes every year, but the vast majority are too weak to be felt. Earthquakes are measured using the moment magnitude scale, which quantifies the energy released. The damage from an earthquake depends on several factors: the magnitude, the depth, the distance from populated areas, and the quality of buildings. Deep earthquakes, even if powerful, cause less surface shaking than shallow ones. Earthquakes also trigger secondary hazards. But earthquakes are natural. Predicting earthquakes is notoriously difficult. Scientists can identify regions where earthquakes are likely, can estimate probabilities over long timescales. But pinpointing when an earthquake will occur is beyond current capabilities. So, we live with earthquakes, preparing as best we can, building structures that can withstand shaking, creating early warning systems, giving seconds or minutes of notice, educating people about what to do when the ground starts to move. And just as the ground can shake beneath us, there are giants of the plant world that have weathered countless such tremors. Redwood trees, found along the coast of California and Oregon, are among the tallest living things on our planet. The tallest known redwood, a tree named Hyperion, stands over 380 feet tall, taller than a 30-story building. Redwoods can live for over 2,000 years, and some individual trees are believed to be even older. The bark of a redwood is thick, fibrous, and resistant to fire. Redwoods also create their own climate. The coastal fogs rolling in from the Pacific is captured by the needles, condensing into droplets that drip down to the ground, providing moisture during the dry summer months. The wood of redwoods is prized for its beauty and durability. Walking through a redwood forest is a unique experience. The trees tower overhead, their trunks so massive it takes several people linking hands to encircle one. And redwoods remind us of the power of conservation. And just as redwoods tower above the forest floor, there are creatures below producing their own light in the darkness. Bioluminescence, the ability of living organisms to produce light, is surprisingly common in the ocean. The light is produced by a chemical reaction, usually involving a molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it produces light. Organisms use bioluminescence for different purposes. One of the most spectacular displays of bioluminescence occurs during blooms of dinoflagellates, a type of plankton. When disturbed, these tiny organisms emit a flash of blue-green light. These bioluminescent blooms are sometimes called milky seas, and they've been reported by sailors for centuries, though they're rare and difficult to study. On land, fireflies are the most familiar bioluminescent organisms. Some species of fireflies even synchronize their flashing, creating waves of light pulsing across the landscape. This synchronization is not fully understood, but it's thought to involve individuals adjusting their flashing based on what they see around them, gradually falling into sync until the entire group is flashing together. Bioluminescence has also inspired technology. So bioluminescence is more than just a curiosity. It's a survival strategy, a communication tool, a source of inspiration, and a reminder the natural world is full of light, even in the darkest places. The deepest point in the ocean is the Mariana Trench, located in the western Pacific. At that depth, the pressure is immense, over 8 tons per square inch, more than 1,000 times the pressure at sea level. And yet, life exists there. In 1960, 2 men descended to the bottom of the Mariana Trench in a submersible called the Trieste, and they reported seeing a flatfish and some shrimp. These deep-sea creatures have evolved unique adaptations. Food in the deep ocean comes from above, in the form of marine snow, tiny particles of organic matter drifting down from the surface. This snow accumulates on the ocean floor, providing a food source for bacteria, which in turn are eaten by larger organisms. The Mariana Trench also contains hydrothermal vents, cracks in the ocean floor where superheated water, rich in minerals, spews out from the crust. Exploring the deep ocean is incredibly difficult, but technology is improving. Remotely operated vehicles, equipped with cameras and sampling tools, can descend to the deepest parts of the ocean, sending back images and collecting samples. And the deep ocean is vast, so the deep ocean remains one of the last great frontiers, a place of mystery and wonder, a reminder our world still has secrets, still has places we've barely touched. And every expedition down there brings back new discoveries, new species, new insights into how life adapts to the most extreme environments on the planet. And while the deep ocean harbors life in darkness, there are partnerships on the surface thriving in the harshest conditions. Lichen is not a single organism. Lichen can grow almost anywhere, on rocks, on trees, on soil, even on man-made structures. Lichen grows slowly, sometimes just a few millimeters per year, but they can live for a very long time. Lichen comes in many forms. Lichen is also an important indicator of air quality. Because they absorb nutrients directly from the air, they're sensitive to pollution. Lichen has been used by humans for thousands of years, but lichen is also fragile. And yet, lichen persists. It's a survivor, adapted to the harshest environments, finding a way to live where almost nothing else can. Walking through a forest or along a rocky shore, it's easy to overlook lichen. And just as lichen preserves life in harsh conditions, there's another substance that preserves moments from the past in perfect detail. Amber is fossilized tree resin, hardened over millions of years into a translucent, golden substance. But amber is more than just pretty to look at. When resin oozes from a tree, it's sticky, and insects, spiders, even small vertebrates can become trapped in it. Amber has been found all over the world, but some of the most famous deposits are in the Dominican Republic and the Baltic region. Studying amber allows scientists to learn about extinct species, about ancient climates, about how ecosystems have changed over time. Some of the insects found in amber are related to modern species, offering clues about how those species evolved. Amber also preserves plant material, leaves, flowers, seeds, even pollen. There's something almost magical about amber. It's a window into the past, a substance holding a piece of history, frozen in time. Amber has also inspired stories and myths, but amber is also scientifically valuable. So amber is more than just a beautiful stone. It's a record, a time capsule, a gift from the ancient forests to us, carrying with it the story of life as it was millions of years ago. And while amber preserves life from ancient forests, there are living wetlands preserving things in their own remarkable ways. Peat bogs are wetlands where dead plant material, mostly moss, accumulates faster than it can decompose. Peat bogs are found in cool, wet climates, particularly in northern regions like Scotland, Ireland, Canada, and Russia. They're important carbon sinks, storing vast amounts of carbon that would otherwise be released into the atmosphere. But peat bogs are also fragile. Peat bogs also preserve things in remarkable ways. Peat has been used as fuel for centuries, particularly in regions where wood is scarce. It's cut from the bog, dried and burned, providing heat for cooking and warmth. Peat bogs are also unique ecosystems, and peat bogs are quiet, eerie places. The ground is soft, spongy, sometimes treacherous, so peat bogs are more than just wetlands. And just as peat bogs preserve the past, there are transformations in nature that show us the power of change. Metamorphosis is one of the most remarkable transformations in nature. This process takes days or weeks, depending on the species. When the transformation is complete, the butterfly emerges, wet and crumpled, and slowly pumps fluid into its wings, expanding them, allowing them to dry and harden. The change is not just physical. Many insects undergo metamorphosis, not just butterflies. Bees, beetles, flies, mosquitoes all go through similar transformations, though the specifics vary. Metamorphosis allows insects to exploit different resources at different stages of their lives. The evolution of metamorphosis is still not fully understood, but it's clearly been successful. And there's something poetic about metamorphosis, about the idea that change is not just possible, but can be total, transformative, creating something entirely new. It's a reminder life is not static, that growth often involves periods of vulnerability, of transition, where the old form must be left behind before the new one can emerge. Watching a butterfly emerge from a chrysalis is a small miracle, a moment when you can see in real time the process of transformation. And just as butterflies undergo transformation, there are frozen landscapes undergoing their own slow changes. Permafrost is ground remaining frozen for at least 2 consecutive years. It's found in polar regions and high mountains, covering about a quarter of the land surface in the northern hemisphere. Permafrost can be hundreds of feet thick, and it contains vast amounts of organic material, plants and animals. that died and froze before they could decompose. This is a concern because permafrost holds an estimated 1,600,000,000,000 tons of carbon, about twice as much as is currently in the atmosphere. Thawing permafrost also affects the landscape. Buildings, roads, pipelines, all built on what was once solid ground, can shift or collapse as the ground beneath them softens. But permafrost also provides a glimpse into the past. Permafrost also contains ice wedges, large masses of ice forming when water seeps into cracks in the ground and freezes, expanding and widening the cracks over time. These ice wedges can create distinctive polygonal patterns on the surface, visible from the air, marking the landscape in ways unique to permafrost regions. And as permafrost thaws, it reveals things frozen for centuries or millennia. So permafrost is more than just frozen ground. And while permafrost preserves the past in ice, there are coastal ecosystems preserving the future in their roots. Mangroves are trees growing in coastal areas, in the zone where land meets sea, their roots submerged in salt water. They're remarkably adaptable, able to tolerate conditions killing most other plants. Mangrove forests are found in tropical and subtropical regions around the world, lining coastlines, forming dense thickets providing habitat for countless species. Mangroves also protect coastlines. Their roots, tangled and dense, slow down waves, reducing erosion and buffering the impact of storms. And mangroves store carbon, lots of it. But mangroves are under threat. Efforts to restore mangroves are underway in many places, recognizing their value, not just for biodiversity, but for coastal protection and carbon storage. Planting mangroves is relatively straightforward, and if conditions are right, they grow quickly, establishing new forests in just a few years. Walking through a mangrove forest is a unique experience. So mangroves are more than just trees. They're ecosystems, protectors of coastlines, carbon stores, and reminders. The boundary between land and sea is not a sharp line, but a transition zone, a place where life has found ways to thrive in conditions seeming impossible. And while mangroves thrive where land meets water, there are vast expanses where water has left behind crystals of salt. Salt flats are vast, flat expanses of ground covered with a layer of salt. The largest salt flat in the world is the Salar de Uyuni in Bolivia, covering over 4,000 square miles. Salt flats are harsh environments. The salt makes the soil inhospitable to most plants. And the flat, open terrain offers no shade, no shelter. Salt flats are also economically valuable. But extracting lithium can be controversial. It requires large amounts of water, which is scarce in these arid regions, and it can disrupt ecosystems and local communities. Salt flats also have a stark beauty. Visiting a salt flat is an experience staying with you. And just as salt flats are shaped by water and heat, there are other features shaped by heat from deep below. Geysers are hot springs periodically erupting, shooting water and steam high into the air. They're rare, found in only a few places around the world, where volcanic activity heats water underground, and where the geology creates the right conditions for an eruption. The most famous geyser is Old Faithful in Yellowstone National Park, which erupts roughly every 90 minutes, sending a column of water over 100 feet into the air. Geysers work through a combination of heat, water, and pressure. Water seeps into the ground, where it's heated by magma or hot rock deep below the surface. After an eruption, the cycle starts again. Geysers are fragile. Yellowstone is home to more geysers than anywhere else on our planet. With over 500 active geysers, about half of all the geysers in the world. The park sits atop a supervolcano, a massive chamber of magma heating the groundwater, creating the conditions necessary for geysers, hot springs, mud pots, and fumaroles. Other geyser fields exist in Iceland, New Zealand, Russia, and Chile, but none are as concentrated or as active as Yellowstone. Watching a geyser erupt is a thrilling experience. There's a moment of quiet, a sense of anticipation, and then the ground trembles. Water begins to surge, and suddenly a column of boiling water shoots into the air, accompanied by a roar of steam. So geysers are rare, spectacular, and a reminder of the heat lying beneath the surface, waiting to be released. And just as geysers reveal the power beneath the surface, there are creatures above demonstrating the power of instinct and navigation. Birds migrate thousands of miles, traveling between breeding grounds and wintering areas, following routes honed over millions of years. Migration is driven by the need to find food and suitable breeding conditions. In the Arctic summer, the days are long, the tundra is alive with insects, and conditions are ideal for raising young. Navigating these long distances requires remarkable abilities. Migration is also dangerous. Birds face predators, storms, exhaustion, and the challenge of finding food and rest along the way. Some migrations are even more extreme. Migration also connects ecosystems, but migration is under threat. Habitat loss, climate change, and obstacles like buildings and power lines all make migration more difficult. So, migration is one of nature's great journeys, evidence of the endurance and navigational skills of birds. And as these birds complete their journeys, traveling between the farthest reaches of our world, we too arrive at the end of this journey tonight. Closing passage. So, wherever you are, allow your mind to rest now. Let your breath slow, deepening with each gentle rise and fall. The journey doesn't end, and you are part of it all. Tomorrow, when you wake, the sun will rise on that same world. The rain will still smell of earth and promise. Sleep well, and thank you for dreaming with us tonight. End of part 1. Facts 1 to 50. Total word count approximately 56,000 words. Duration 60 minutes. Status complete. This completes part 1 of the most relaxing facts about Earth to fall asleep. 2. All 50 facts delivered following master plan specifications. The most relaxing facts about Earth to fall asleep. To part 2. Facts under 51,100. Duration 60 minutes. Word count. Target 50,000, 60,000 words. Narrator Matthew Gray. Note: this is part 2, continuing after user confirmation of part 1 completion. The oldest living individual tree on our planet is a bristlecone pine in California's White Mountains. Scientists call it Methuselah, and it has been growing for over 4,800 years. But Methuselah is not alone. Slow growth means dense wood, resistant to rot and insects. The exact location of Methuselah is kept secret, protected from those who might damage it. Visitors can walk through the grove, surrounded by ancient bristlecones, but they won't know which one is the oldest. And there's something humbling about standing near such an old living thing. Other bristlecones in the area have died, their wood preserved by the dry air, standing as ghostly sculptures for thousands of years after death. These dead sentinels remind us that even the longest lived things eventually end, but also that their presence, their form, can persist long after life has departed. So these trees are more than just old. And just as these ancient trees connect us to the distant past, there are stones on our planet that have traveled even further through time. Meteorites are pieces of asteroids or comets that have fallen to our planet's surface. These rocks are older than anything found naturally on the surface here. While our oldest surface rocks are around 4 billion years old, some meteorites date back 4.5 billion years, to the very formation of the solar system. Scientists study them to understand what the early solar system was like, what elements were present, how planets formed. Others contain organic compounds, amino acids, the building blocks of life. This suggests that the ingredients for life may have been delivered to our world by impacts, seeding the young planet with the molecules needed for biology to begin. Most meteorites are small, weighing just a few grams. Larger impacts are rare but dramatic, but most meteorite falls are harmless. They land in remote areas, sink into oceans, or are simply never found. So, meteorites are messengers, carrying information from the depths of space and time. And, while these cosmic visitors bring material from beyond, there are formations on our world built entirely from within. Stalactites and stalagmites, those stone formations found in caves, grow at a pace measured in centuries. A stalactite hangs from the ceiling, formed by water dripping down and depositing minerals. The difference between them is easy to remember. Stalactites have to hold on tight to the ceiling, while stalagmites might reach up to meet them. Each drip of water carries dissolved minerals, usually calcium carbonate, picked up as rainwater seeps through limestone. The rate of growth depends on several factors: how much water is dripping, how much mineral it contains, the temperature of the cave. In some caves, stalactites grow less than 1/10 of an inch per century. Some are enormous, extending dozens of feet from ceiling to floor. Colors vary depending on the minerals present. Iron oxides create reds and oranges. Caves with stalactites and stalagmites are fragile environments. So, when visiting such caves, it's important to stay on designated paths, to look but not touch, to respect the slow work of water and time. And while water shapes stone from above, there are forces beneath the surface creating entirely different landscapes. Sinkholes form when the ground suddenly collapses, creating a hole that can swallow buildings, cars, entire sections of road. They happen in areas with soluble rock, like limestone, where underground water gradually dissolves the stone, creating cavities below the surface. For years, sometimes centuries, these voids grow larger, with only a thin layer of soil or rock covering them. Some sinkholes form slowly, gradually settling over weeks or months, giving warning signs like cracks in the ground or tilting structures. Others form suddenly, without warning, collapsing in seconds. The size varies widely. Sinkholes are more common in certain regions. Human activity can increase the risk. Pumping groundwater lowers the water table, removing the support that kept the cavities stable. But sinkholes are also natural features of karst landscapes, the term for regions where soluble rock has been shaped by water. So sinkholes remind us that the ground beneath our feet is not always solid, that hidden cavities may exist below, and that what seems stable today might not be tomorrow. They're openings into a hidden world, connections between the surface and the depths, and they demonstrate the ongoing work of water reshaping our planet from within. And just as water opens doors beneath us, there are doors in the sky that close each day with spectacular displays. Sunsets are red because of the way light interacts with the atmosphere. But at sunset, the sun is low on the horizon, and its light must travel through much more atmosphere to reach us. The intensity and variety of colours depend on what's in the atmosphere. Dust, pollution, and water vapour all affect how light scatters. Clean air produces paler sunsets with softer colours. Clouds add another dimension. They catch the light, reflecting and refracting it, creating layers of colour. The opposite phenomenon occurs at sunrise, though most people see fewer sunrises than sunsets, and sunsets have always captured human attention. So sunsets are more than just pretty. They're lessons in physics, demonstrations of how light behaves, reminders that beauty often emerges from the simplest interactions between fundamental forces. And just as the sky changes colour with the setting sun, there are places where the water itself glows with colour. Some lakes are pink. The colour comes from microorganisms, usually a type of algae called Dunaliella salina, which produces carotenoids, the same pigments making carrots orange. These algae thrive in very salty water, conditions most other organisms can't tolerate. Lake Hillier in Australia is one of the most famous examples. Retba, or Lac Rose, in Senegal is another. Pink lake, its colour varying with the season, becoming more intense during the dry season when salinity increases and algae populations boom. These lakes are usually highly saline, sometimes saltier than the ocean. This high salt content creates the harsh conditions favouring the pink algae while excluding most other life. The pink isn't harmful, but these lakes are fragile. Changes in water chemistry, whether from pollution, climate, or alterations in water flow, can affect the algae populations and change or eliminate the pink colour. So, pink lakes are beautiful anomalies, places where biology and chemistry combine to create something unexpected. And while some water is coloured by life within it, there are places where the earth itself is painted in vivid hues. The Grand Prismatic Spring in Yellowstone National Park is the largest hot spring in the United States and the third largest in the world. These colours come from different types of bacteria, living at different temperatures. The centre is too hot for most life, reaching temperatures around 189 degrees Fahrenheit, close to boiling. But as the water flows outward and cools, conditions become suitable for thermophilic bacteria. Organisms adapted to live in extremely hot water. The orange and red bacteria on the outer edges live in water around 130 degrees Fahrenheit. These species produce pigments, protecting them from sunlight and helping them absorb energy. The spring is fed by water heated by the volcanic system beneath Yellowstone. Viewing the spring from ground level is impressive, but the full pattern is best seen from above. The spring is delicate. Stepping off the boardwalks can damage the bacterial mats, and throwing objects into the water introduces contaminants that can alter the chemistry and harm the organisms. So this spring is a living painting, an intersection of geology and biology, where heat from deep within creates the conditions for colourful life to thrive. And while this spring demonstrates life thriving in heat, there are other places where life exists in the opposite extreme. Antarctica is the coldest place on our planet. The lowest temperature ever recorded was minus 128.6 degrees Fahrenheit at the Soviet Vostok station in 1983. But even in this extreme cold, life exists. The continent is almost entirely covered by ice, some of it more than 2 miles thick. But Antarctica isn't just ice. There are mountains hidden beneath the sheet, some of them among the highest on the planet. The continent is also remarkably dry. Wildlife is limited, but specialized. Penguins are the most famous residents, adapted perfectly to the cold, with thick layers of blubber and dense feathers keeping them warm. No land mammals live there, and no indigenous human population has ever existed. And yet, it's also beautiful. So, Antarctica is an extreme, a place pushing the limits of what life can endure. It's a frozen archive, holding ice cores containing bubbles of ancient air, allowing scientists to study climate history going back hundreds of thousands of years. And while Antarctica represents one extreme of cold, there are underwater features representing another extreme of heat. Hydrothermal vents are cracks in the ocean floor where superheated water, sometimes reaching temperatures over 700 degrees Fahrenheit, gushes out from beneath the crust. Cold seawater seeps down through cracks, gets heated by magma, and then rises back up, carrying dissolved minerals. When this hot water meets the cold ocean, the minerals precipitate, forming chimneys of rock around the vents. What makes these vents remarkable is not just the heat, but the life surrounding them. The basis of these ecosystems is chemosynthetic bacteria. Giant tube worms are among the strangest inhabitants. They have no mouth, no digestive system. These ecosystems were only discovered in 1977 during a deep-sea expedition exploring the Galapagos Rift. It also raised questions about the origin of life. Could life have begun at such vents, protected from harsh surface conditions on the early planet, using chemical energy instead of sunlight? Vents don't last forever, so hydrothermal vents are oases in the deep, places where heat and chemicals from the interior support life in the cold, dark depths. And while vents represent one type of extreme environment, there are other places where chemistry creates conditions equally challenging. Acid lakes exist in several volcanic regions. Their waters so acidic they can dissolve metal and burn skin. These extreme bodies of water form when volcanic gases, particularly sulfur dioxide and hydrogen sulfide, dissolve in water, creating sulfuric acid and other corrosive compounds. Kawah Ijen in Indonesia is home to one of the most acidic lakes on our planet, with a pH around 0.5, similar to battery acid. These lakes are hot, often close to boiling, heated by volcanic activity below. Steam rises from the surface, carrying acid droplets that can damage lungs if inhaled. Despite the extreme conditions, some life exists even here. Studying these organisms provides insights into the limits of life, into the biochemical adaptations, allowing survival in conditions that would destroy most cells. Acid lakes also pose hazards. The water can breach containment if the volcanic crater is damaged, flowing downhill and contaminating rivers. But these lakes are also beautiful in a harsh, alien way. So acid lakes represent another extreme, another edge of where life can persist. They're laboratories for studying extremophiles, windows into volcanic processes, and the warnings about the power of chemistry to transform landscapes. Salt domes are massive underground structures formed when ancient salt deposits, buried under layers of sediment, begin to rise. These structures form over millions of years. Some break through to the surface, creating salt mountains or salt glaciers, where the mineral flows out onto the landscape. More commonly, they remain underground, detectable only through seismic surveys or drilling. Salt domes trap oil and natural gas. These caverns, carved into salt domes, are used to store oil, natural gas, and other materials. Salt is impermeable to liquids and gases, making it ideal for storage. But salt domes also pose risks. The movement of these structures is ongoing, though incredibly slow. And just as salt flows underground, there are places where stone appears to flow on the surface, in patterns seeming almost deliberate. Stone stripes are patterns of rocks arranged in parallel lines, running down hillsides in polar and alpine regions. From above, they look like someone drew stripes on the landscape, alternating between rocky areas and areas with finer soil. When water in the soil freezes, it expands, pushing rocks upward and outward. On flat ground, this process creates stone polygons, roughly circular or hexagonal patterns, with rocks outlining the edges and finer soil in the centers. On slopes, gravity pulls everything downhill, stretching the polygons into stripes, sometimes extending for hundreds of feet down the mountainside. These features are common in areas experiencing periglacial conditions, places cold enough for regular freeze-thaw cycles, but not so cold that everything stays frozen year-round. Indigenous peoples in the Arctic have known about these patterns for millennia, incorporating them into navigation and storytelling. The size varies depending on the rocks available and the intensity of freeze-thaw cycles. Some stripes are just a few inches wide. Studying these features helps scientists understand periglacial processes, which were much more widespread during ice ages. So stone stripes are another example of nature's ability to create order from chaos, to take random distributions of rocks and, through simple physical processes repeated endlessly, arrange them into patterns. They're beautiful in their regularity, fascinating in their formation, and revealing about the power of freeze-thaw cycles to reshape landscapes. And while ice arranges stones on hillsides, it creates entirely different features when combined with wind and erosion. Ice caves form in glaciers, carved by meltwater flowing through the ice. The walls glow blue, a color coming from the way ice absorbs light. These structures are temporary. They change every year as the glacier moves and melts, creating new passages and collapsing old ones. Sunlight filtering through translucent walls creates a diffuse, otherworldly illumination. Some are large enough to walk through, with chambers spacious enough for dozens of people. Others are tight squeezes, requiring crawling through narrow passages. In winter, these spaces become less accessible and more dangerous. Ice caves are found wherever glaciers exist, from Alaska to Iceland to the Alps, and they're ephemeral. A cave existing today might be gone next year, replaced by different passages as the glacier evolves. So these spaces are windows into a frozen world, places where the beauty of ice is on full display. And just as ice creates temporary beauty, there are crystals in caves that grow in darkness over immense spans of time. The Cave of Crystals in Mexico contains some of the largest natural crystals ever found. These selenite crystals, a form of gypsum, are enormous, some over 30 feet long and weighing as much as 55 tons. The conditions were perfect for crystal growth. The chamber was discovered in 2000 during mining operations in Nacre, Chihuahua. Exploring it is difficult. The temperature is extreme and the humidity is 100%. The crystals themselves are fragile, despite their size. There's discussion about reflooding the chamber to preserve them, but this would make access impossible. It's a dilemma. Keep it accessible for study and wonder, allowing continued exposure to air that may degrade them, or protect them by returning to the water, but losing the ability to observe and study them directly. Other crystal caves exist, but none match the sheer size of the Nacre crystals. And they remind us that beneath the surface, in hidden chambers we rarely see, nature has been creating wonders for eons. So these crystals are gifts from deep time, products of patience and perfect conditions. They're evidence that extraordinary beauty can emerge from simple chemistry, given enough time. And while these crystals grew in warm chambers, there are formations in cold places that tell equally remarkable stories. Ice wedges form in permafrost when temperature fluctuations cause the ground to crack. From above, these structures create distinctive polygonal patterns on the landscape, similar to stone polygons, but on a much larger scale. The patterns can be seen from aircraft or satellites, marking the tundra with geometric shapes stretching across miles of terrain. These features are common in the Arctic and in Antarctica, anywhere permafrost is extensive and temperatures fluctuate seasonally. The polygons often have raised edges where the ice wedges push up the soil, and depressed centers where the ground has settled. As climate warms, permafrost is thawing and ice wedges are melting. When they do, the polygons collapse, creating dramatic changes in the landscape. Studying ice wedges helps scientists understand permafrost dynamics and predict how these environments will respond to continued warming. And they're ancient. Some formed thousands of years ago and have been growing slowly ever since. So these structures are more than just cracks filled with ice. And while ice shapes the land in cold regions, there are places where lack of water creates equally distinctive landscapes. Badlands are dry, eroded regions where soft, sedimentary rock has been sculpted by water and wind into complex landscapes of gullies, ridges, and pinnacles. These formations typically develop in areas with little vegetation, where there's nothing to hold the soil together. When rain falls, it runs off quickly, cutting deep channels. The colours can be spectacular. Badlands are treasure troves for paleontologists. The rapid erosion constantly exposes new fossils, washing them out of the rock and leaving them on the surface. Drainage patterns in these areas are dendritic, branching like trees, with countless small gullies feeding into larger channels. Life in Badlands is harsh, but not absent, and there's a stark beauty to these places. The shapes, the colours, the sense of a landscape constantly being reshaped by erosion, all create scenery that's dramatic and otherworldly. So Badlands represent landscapes in rapid change, places where erosion works faster than almost anywhere else, where geological processes visible elsewhere only over millions of years happen in centuries or decades. And while Badlands show us landscapes actively eroding, there are other places where the ground simply vanishes beneath our feet in more dramatic fashion. Quicksand is a mixture of sand and water that behaves like a liquid when disturbed. It forms when water saturates loose sand, reducing friction between grains. Contrary to popular depictions in movies, quicksand doesn't actually suck you down or swallow you whole. It forms in several environments: riverbanks, beaches, marshes, anywhere water can saturate loose sediment. Escaping requires understanding the physics. Thrashing makes it worse, working you deeper into the mixture. Once you stop moving, the sand tends to resettle, becoming more viscous, which makes movement harder. Quicksand was much more feared historically, with stories of travellers being swallowed by it, horses lost, wagons stuck. Modern understanding has demystified it somewhat, showing it's dangerous but manageable if you know what to do. Animals instinctively understand to spread their weight, so quicksand is a reminder that solid ground isn't always solid, that appearances can be deceiving, and that understanding the physics of materials can be life-saving. And while quicksand is a temporary trap, there are places where the Earth's forces create permanent passages through solid rock. Natural arches form when rock is eroded away, leaving behind graceful spans of stone. Wind, water, and chemical weathering work on weak points in the rock, gradually hollowing out openings that grow larger over thousands of years until an arch remains, supporting itself through compression and the strength of the remaining material. The process begins with cracks or areas where the rock is softer or more fractured. Eventually, an opening breaks through, creating the characteristic hole. From there, the forces continue working, enlarging the opening, thinning the remaining rock. Utah's Arches National Park contains over 2,000 of these features, more than anywhere else on the planet. These structures aren't permanent. Some are massive, like Landscape Arch, spanning over 280 feet, one of the longest natural stone spans in the world. Others are small, barely large enough to walk through. Indigenous peoples in the Southwest considered many of these formations sacred, incorporating them into creation stories and using them as landmarks. And they're undeniably beautiful. The way they frame the landscape, the colors of the stone, the interplay of light and shadow as the sun moves across the sky, all combine to create scenes that have inspired photographers, painters, and travelers for generations. So natural arches are sculptures created by time and elements, evidence that erosion can be an artist as well as a destroyer. And while arches demonstrate erosion's power to shape stone, there are places where water has carved even more. Extensive networks underground. Underground rivers flow through darkness, carving passages through rock, sometimes traveling for miles without ever seeing sunlight. Some are accessible through caves, where explorers can follow them through chambers and passages. Others are completely hidden, only revealed through tracer studies, where dye is poured into sinkholes and reappears at springs miles away, proving the connection. These rivers can be substantial, carrying significant volumes of water. Fish and other aquatic creatures live in some of these rivers, species that have adapted to permanent darkness. They're often blind, having lost their eyes over evolutionary time, navigating instead through other senses. The water is typically very pure, filtered through layers of rock. Underground rivers play important roles in hydrology, connecting surface water systems in ways not obvious above ground. Pollution that enters an underground river system can travel far and contaminate areas seemingly unconnected to the source. Chemicals, sewage, or other contaminants can move through these systems rapidly, emerging at springs used for drinking water or supporting ecosystems. Some underground rivers are massive, so these rivers are hidden arteries, moving water through the subsurface, shaping landscapes from within. They're reminders that not all rivers flow in sunlight, that beneath the ground is a three-dimensional world of water in motion, and that the division between surface and subsurface is more permeable than we might think. And just as water flows hidden beneath stone, there are sounds that travel through the ground in ways we're only beginning to understand. Infrasound, sounds at frequencies below human hearing, travels through air, water, and ground. These low-frequency sounds travel farther than higher frequencies, bending around obstacles, propagating over great distances with less energy loss. Whales also use infrasound, their songs containing components below human hearing. These deep sounds can travel hundreds or even thousands of miles through ocean water, allowing individuals to stay connected across vast expanses. Natural phenomena produce infrasound as well. Humans can't consciously hear infrasound, but we may be able to sense it. Some researchers suggest certain frequencies can produce feelings of unease or fear, possibly explaining why some places feel haunted or uncomfortable. Wind blowing over hills or through valleys can generate infrasound. Studying infrasound has practical applications. So infrasound is a hidden channel of communication and information, used by animals, generated by natural processes, and offering humans tools for monitoring the world. It reminds us that our senses capture only a portion of what's happening around us, that reality extends beyond what we can directly perceive, and that listening carefully with the right tools can reveal layers of activity we otherwise miss entirely. Bioluminescent bays are bodies of water glowing at night, filled with dinoflagellates that emit light when disturbed. When you move through the water, swimming or paddling a kayak, every motion triggers flashes of blue-green light. The wake behind a boat glows. These dinoflagellates produce light through the same chemical reaction used by many other bioluminescent organisms. The bays that support such populations need specific conditions. Pollution and development threaten these environments. Light pollution from nearby development can affect the organisms. Conservation efforts aim to protect remaining bioluminescent bays. The experience of being in a glowing bay is profound. The darkness of the night, the silence of the water, and then the sudden appearance of light with every movement create moments that stay with people. So these bays are treasures, places where biology creates visible magic. And while some water glows with life, there are places where water itself seems to defy gravity. Reversing waterfalls occur when strong winds or tides force water upward, making it appear to flow backward. The phenomenon requires specific conditions: strong upward air currents and a narrow waterfall, where the volume of water is small enough for wind to influence. When these conditions align, the water streaming down gets caught by the upward moving air, blown back up the cliff face, sometimes disappearing entirely as it's atomized into mist. It's temporary and weather dependent. Similar effects occur in other locations with the right geography. Coastal cliffs, particularly those facing prevailing winds, sometimes see their waterfalls reversed during storms. Tidal effects can also reverse flows, though in a different way. These phenomena capture imagination because they seem to violate what we expect, and they remind us that nature isn't bound by our expectations. The forces governing our world, gravity, wind, tides, all interact in complex ways. So reversing waterfalls are examples of nature's playfulness, moments when conditions align to create something unexpected. And while wind can push water upward, there are places where water seems to disappear into the ground entirely. Lost rivers are watercourses that flow for a distance, then vanish underground, reappearing miles away as springs. This happens in karst landscapes, where limestone bedrock contains caves and passages allowing water to travel beneath the surface. The Lost River in Indiana is a classic example. Tracing these flows helps hydrogeologists understand groundwater systems. These hidden flows complicate water management. Pollution entering the river where it's visible can emerge miles away at springs, contaminating water sources seemingly unconnected to the pollution source. Historically, lost rivers were mysterious. their disappearance unexplained. Some places have multiple rivers, vanishing and re-emerging, creating landscapes where surface water seems ephemeral. You might follow a stream, see it disappear, then encounter another stream, miles away, that genetic testing reveals is the same water, having travelled through darkness between appearances. These systems are also habitat for unique species, blind fish and cave-adapted invertebrates living in the underground portions. So lost rivers are reminders that what we see isn't always the full story. And while some water flows hidden through caves, there are places where the ground itself seems to breathe. Breathing caves are caverns where air flows in and out in response to atmospheric pressure changes. When pressure outside drops, air flows out of the opening, sometimes strongly enough to blow out candles or rustle vegetation near the entrance. This happens because large cave systems contain significant volumes of air. Some caves breathe more obviously than others. Those with large internal volumes and relatively small openings show the strongest effects. Temperature differences also drive airflow. In winter, the process reverses. These air movements affect the internal environment. They regulate temperature and humidity, influence how quickly evaporation occurs from cave formations, and can even affect the chemistry of water dripping from the ceiling, changing how quickly stalactites and stalagmites grow. Early explorers found these caves unsettling, so breathing caves are demonstrations of how air pressure, volume, and temperature interact. They show us that caves aren't isolated spaces, but dynamic systems connected to the atmosphere, responding to weather, exchanging air, and creating flows that can surprise anyone expecting the underground to be still and lifeless. And while caves breathe with the weather, there are sounds in nature that carry across distances in surprising ways. Acoustic shadows are areas where sound doesn't reach, blocked by terrain, wind patterns, or temperature layers in the atmosphere. This happens because sound waves bend as they travel through air with varying temperature or wind velocity. The result is that distance and loudness don't always correlate. Sometimes people close to a sound source hear nothing, while distant observers hear it clearly. Modern examples include communities near airports, sometimes experiencing varied noise levels, seemingly defying logic. Whales exploit similar principles, using ocean layers with different temperatures and salinities to channel sound over great distances. They position themselves in sound channels where their songs travel farther with less energy loss, communicating across hundreds of miles by working with, rather than against, the ocean's structure. Wind farms sometimes create acoustic shadows, with turbine noise reaching some homes but not others, even when the homes are similar distances away. So acoustic shadows remind us that sound doesn't travel simply and predictably. And just as sound can be blocked or channeled, light behaves in equally surprising ways under certain conditions. Auroras don't just occur near the poles. During intense solar storms, they can be seen much closer to the equator, sometimes appearing over populated areas where they're normally never visible. The aurora is controlled by the magnetic field, which funnels charged particles from the solar wind toward the poles. In 1859, the Carrington event, the largest recorded solar storm, produced auroras visible as far south as the Caribbean. The lights were so bright, people reported being able to read newspapers by their glow. If such an event occurred today, the impact would be far more severe. Scientists monitor the sun constantly, watching for signs of solar storms, Lesser storms occur more frequently, causing minor disruptions. Airline pilots flying polar routes are warned about increased radiation exposure, and they create beauty. So, auroras, while normally polar phenomena, can occasionally extend their range, creating rare opportunities for many more people to witness them. These events are reminders that we live in a solar system, not in isolation, and that our star's activity affects us in ways both beautiful and potentially dangerous. And while auroras paint the night sky, there are places where the stars themselves seem to vanish. Light pollution has erased the Milky Way from view for most of humanity. This is a recent change. The effects go beyond aesthetics. Many animals navigate by the night sky, their behavior disrupted by artificial light. Plants and insects also suffer. Human health is also affected. Our bodies evolved with natural light cycles, producing melatonin in darkness to regulate sleep. But light pollution is reversible. Dark sky preserves. Areas protected from light pollution allow people to experience truly dark nights. Experiencing this creates perspective. Seeing the scale of our galaxy, realizing every visible star is a sun, understanding we're part of something vast, all produce feelings that can be profound, even transformative. So, light pollution is both a practical problem and a philosophical one. And while we've brightened our nights, there are places where darkness is so deep that no light reaches at all. The ocean's midnight zone, extending from about 3,000 to 13,000 feet deep, exists in perpetual darkness. No sunlight penetrates that far. Organisms here live under immense pressure, over 3,000 pounds per square inch at the top of the zone, increasing with depth. Many fish here are black, absorbing any stray photons to remain invisible. The anglerfish, perhaps the most iconic inhabitant, has a bioluminescent lure dangling in front of its mouth. Smaller fish, attracted to the light, swim closer to investigate and are snatched up. Many species exhibit bizarre adaptations. Reproduction is also challenging. Finding a mate in vast, dark waters is difficult. Scientists explore this zone using submarines and remotely operated vehicles. What we have found challenges assumptions about where life can exist. So, this zone is a reminder that our world contains vast regions unknown, places where conditions seem impossible, but life persists. The deep ocean remains one of our planet's last frontiers, holding secrets, species, and ecosystems we're only beginning to glimpse. And while the deep ocean exists in darkness, there are places on land where light behaves in ways seeming almost magical. Sundogs are bright spots appearing beside the sun, caused by ice crystals in the atmosphere refracting light. The spots often show colors: red closest to the sun, then orange, yellow, and white farther out, like small rainbows flanking the main light source. When conditions are perfect, they're bright enough to be mistaken for second and third suns, creating a truly surreal sight. They're not rare, but most people don't notice them. Sometimes they appear as part of larger displays. Ancient people saw these displays as omens. Multiple suns in the sky seemed impossible, therefore significant. Messages from gods or warnings of coming events. Similar phenomena occur with the moon. Pilots and photographers particularly appreciate sundogs. For pilots, they're indications of ice crystals in the atmosphere, which can be important information for flight planning. So sundogs are optical gifts, moments when ice and light collaborate to create beauty. And while ice crystals create light patterns above, there are patterns in nature formed by forces acting over vastly longer timescales. Hexagonal columns form when basalt lava cools and contracts, creating cracks that propagate through the rock in a remarkably regular pattern. The Giant's Causeway in Northern Ireland is perhaps the most famous example. 40,000 interlocking columns, some over 40 feet tall, cover the coastline, creating a landscape seeming too geometric to be natural. The hexagonal shape is a result of how cracks form in contracting material. It's the same reason honeybees build hexagonal cells, and why soap bubbles packed together form hexagonal patterns. Nature, optimizing for efficiency, repeatedly chooses this shape. The columns form perpendicular to the cooling surface. Erosion exposes these structures, wearing away surrounding material, leaving the harder columns standing. These formations attract geologists, artists, and tourists. They're accessible examples of volcanic processes, teaching tools demonstrating how rocks form and erode. So, hexagonal columns are lessons in material science, demonstrations of how uniform processes create ordered structures. Fairy circles are mysterious bare patches in grasslands, perfectly circular areas where nothing grows, surrounded by rings of taller vegetation. They occur in Namibia and parts of Australia, creating patterns visible from the air. Thousands of circles dotting the landscape in regular distributions that seem almost deliberate. For decades, scientists debated their cause. Recent research suggests both factors might be involved, working together. These circles can last decades, maintaining their shape and size for years before eventually disappearing. New ones form nearby, creating a dynamic landscape where patterns shift, but the overall appearance remains consistent. Indigenous peoples in Namibia have known about them forever, incorporating them into stories. The circles aren't just curiosities. They provide insights into how ecosystems organize themselves, how competition and cooperation create spatial patterns, and how we can detect self-organization in nature. And they remind us that not everything has simple explanations. So fairy circles are mysteries largely solved, but still intriguing, patterns emerging from the interaction of life, soil, and water. And while these circles form from plants competing for resources, there are places where plants cooperate in surprising ways. Nurse trees are species that shelter and protect seedlings of other species, creating conditions allowing them to grow where they couldn't otherwise survive. In harsh environments, young plants often can't establish in open areas. This is common in deserts, where saguaro cacti often grow under mesquite trees or palo verde. The relationship isn't always one way. Sometimes, the nurse benefits from having other plants nearby, creating microclimates that conserve moisture, or providing food for pollinators that also visit the nurse. In forests, similar dynamics occur. This facilitation is important for understanding how ecosystems recover after disturbance. It challenges the idea that nature is only competition. While organisms do compete, they also cooperate, facilitate, and create conditions for others. Restoration ecologists use this knowledge, deliberately planting nurse species to help restore degraded areas. So, nurse trees teach us that even plants, lacking consciousness or intent, can help each other. The relationships emerge from physical and biological processes, from shade and moisture and protection, but the result looks like care. And while nurse trees help by providing shelter, there are organisms that help by connecting plants in networks spanning entire forests. Mycorrhizal networks the underground fungal connections between trees transfer not just nutrients, but also warning signals and even resources from strong trees to weak ones. These networks also redistribute resources. Mother trees, the large old individuals at the center of networks, appear to direct resources preferentially toward their offspring. They recognize kin through chemical signals and allocate more resources to related seedlings than to unrelated ones. The implications are profound. This changes forest management. Instead of viewing forests as tree farms, where individuals are commodities to be harvested, we must see them as ecosystems, where relationships matter as much as individuals. The networks extend beyond trees. These systems are ancient, and it's still not fully understood. Research continues to reveal new aspects of these networks, new ways plants interact through them, new chemical signals and resource transfers. So, mycorrhizal networks are biological internet, connecting individuals, facilitating communication, enabling cooperation that makes forests healthier and more resilient. And while fungi connect trees underground, there are partnerships above ground that shape entire landscapes. Keystone species have disproportionate effects on their ecosystems. Remove them, and the entire community changes, often collapsing into something much simpler. When otters are present, they keep urchins in check, allowing kelp to thrive. Wolves show similar effects. The effects rippled further. Streamside vegetation recovery reduced erosion, changed stream dynamics, affected fish. These examples illustrate that ecosystems aren't just collections of species, but networks of interactions. Conservation increasingly focuses on keystone species, recognizing that protecting them protects the communities they support. It's more efficient than trying to protect every species individually, and acknowledges that some species, through their ecological roles, are more important than their numbers suggest. But identifying keystones isn't always easy. Understanding these relationships requires careful observation and often decades of research. So keystone species teach us that not all species are equal in their ecological importance, that some punch above their weight, and that conservation must consider relationships and functions, not just species lists. They remind us that ecosystems are built on connections, and severing the right connection can bring down the entire structure. And while some species shape ecosystems through their presence, others leave legacies long after they're gone. Ghost forests are stands of dead trees killed by saltwater intrusion. These forests are expanding all along coastlines, particularly on low-lying areas of the Atlantic coast. Ghost forests are appearing as rising seas push saltwater farther inland. The process is gradual at first. These landscapes are transitional. They're also habitat. Dead standing trees provide nest sites for woodpeckers and other cavity nesting birds. Studying these areas helps scientists understand how ecosystems respond to sea level rise, how quickly transitions occur, and what might happen to other coastal forests as conditions change. And they're reminders of what we stand to lose. Coastal forests provide timber, wildlife habitat, storm protection, and carbon storage. For people living nearby, ghost forests are unsettling. So ghost forests are ecological tombstones, showing us where forests died and why. And while some forests die from salt water, there are trees that have found ways to thrive in salty environments. Mangroves have evolved remarkable adaptations for living where land meets sea. Their roots filter salt from the water, allowing them to thrive in conditions lethal to most plants. The root systems are equally impressive. Mangrove forests are nurseries for marine life. The tangled roots provide shelter where young fish can hide from predators, where shrimp and crabs can find food and protection. They also protect shorelines. Carbon storage in these forests is exceptional, but they're threatened. Coastal development, aquaculture, and pollution have destroyed about half the world's mangrove forests in the past 50 years. Restoration efforts are underway in many places. These forests challenge our categories. They're neither fully terrestrial nor fully marine, but exist in the transition zone, adapted to tolerate both. So mangroves are more than just trees in salt water. And while mangroves thrive where salt water meets fresh, there are other boundary zones where different types of water interact in dramatic ways. Haloclines are sharp boundaries between water layers with different salt content. Divers experience these boundaries as sudden changes in visibility and sensation. Swimming through a halocline feels like passing through a membrane. In some cenotes in Mexico, these boundaries are dramatic. These stratified systems are ecologically important. Different organisms inhabit different layers, creating vertical zonation within the same body of water. Haloclines affect water circulation. Climate change is affecting these boundaries. In the Baltic Sea, a permanent halocline separates brackish surface water from saltier deep water. This has existed for thousands of years, shaping the ecology of the entire sea. So haloclines are invisible boundaries with real effects, separating water bodies into layers with different properties and inhabitants. And while haloclines separate water vertically, there are places where different water bodies meet horizontally with equally dramatic effects. The meeting of waters in Brazil is where the Rio Negro and the Amazon River converge, flowing side by side for miles without mixing. The waters are different colors. The Negro dark brown or black, the Amazon sandy brown, and the boundary between them is sharp, a visible line where the two rivers touch but don't blend. This happens because the rivers have different densities, temperatures, and flow velocities. Similar phenomena occur elsewhere. These meetings are visually striking. Seeing two rivers flowing together but remaining separate challenges our expectations. Indigenous peoples recognize these phenomena, incorporating them into place names and stories. These confluences also affect ecosystems. Fish species from one river may not immediately enter the other, respecting the boundary, even though no physical barrier exists. Eventually, the rivers do mix completely, their waters becoming indistinguishable. So these meetings remind us that not all mixings are immediate, that differences can persist even when things come together, and that nature creates visual demonstrations of physics principles we might otherwise never see. And while some boundaries are visible in water, there are less obvious boundaries in the air that have equally powerful effects. The jet stream is a narrow band of very fast winds flowing high in the atmosphere, typically around 30,000 feet. These rivers of air can reach speeds over 200 miles per hour, circling the globe in wavy patterns, steering weather systems, influencing temperatures, and affecting everything from airline routes to crop yields. The position and strength vary with seasons. Recent research suggests climate change is affecting the jet stream, making it wavier, causing it to meander more. This can create blocking patterns where weather systems stall, leading to prolonged heat waves, droughts, or flooding. The waviness matters because it determines how far cold polar air penetrates south and how far warm tropical air extends north. pilots use the jet stream, timing flights to catch tailwinds or avoid headwinds. The jet stream also transports materials. Dust from the Sahara can cross the Atlantic in days, carried by upper-level winds. Understanding the jet stream is important for weather forecasting, and it's not unique to our planet. Jupiter has multiple jet streams, visible as the bands circling the planet. So, the jet stream is an atmospheric river, invisible but powerful, shaping weather across continents. And while the jet stream connects distant places through air, there are connections through Earth itself that link regions in unexpected ways. Antipodes are points on opposite sides of our planet, but some places do have land antipodes. Parts of Spain and Portugal are opposite New Zealand. The concept has fascinated people for centuries. In practice, antipodes are curiosities. Few people visit their antipodal points, though some cities have created sister relationships with their antipodes, connecting places literally on opposite sides of the world. The concept also illustrates how we think about our world. For seismic waves from earthquakes, antipodes are significant, and there's poetry to the idea that for every point on our world, there's an opposite, a place experiencing night when you experience day, winter when you experience summer, a location sharing your planet, but in the most distant relationship possible while still being on the same sphere. So, antipodes remind us that our world is round, that every location has an opposite, and that even the most distant places are connected through the planet itself. They're geographical curiosities, teaching tools for understanding spherical geometry, and reminders that opposite side of the world is not just a figure of speech, but a real location you could theoretically reach by traveling straight through. The Great Blue Hole in Belize is a massive underwater sinkhole, nearly 1,000 feet across and over 400 feet deep. Divers exploring it find stalactites hanging from underwater ledges, formations that could only have grown in air, proving the chamber was once dry. The formations angle oddly, evidence of tilting that occurred after they formed, likely from tectonic shifting. The water inside is exceptionally clear in the upper levels, allowing visibility that extends for over 100 feet. Few organisms live in the deep portions. Scientists have studied it to understand ancient climate. Sediment cores from the bottom contain layers representing different time periods, preserving pollen, minerals, and other materials that reveal what conditions were like when each layer was deposited. The site has become famous, featured in documentaries and attracting divers from around the world. So, this sinkhole is a window into the past, a geological feature revealing how sea levels and climates have changed. It's a dramatic example of how landscapes transform over time, how what's underwater today was once land, and how the forces shaping our planet continue to create remarkable features we're still discovering and studying. And while this blue hole reveals history through its structure, there are crystals that reveal history through their composition. Zircon crystals are among the oldest materials on our planet's surface. These crystals form in molten rock, crystallizing from magma as it cools. What makes them scientifically valuable is that they contain uranium, which decays to lead at a known rate. By measuring the ratio of uranium to lead, scientists can determine when the crystal formed. The oldest zircons tell us important things about early planetary history. These ancient crystals are found in Western Australia, in a rock formation called the Jack Hills. Thousands of zircons have been analysed from this site, each providing a small window into deep time. Zircons are also beautiful. Finding ancient zircons requires careful work, so these tiny crystals are time capsules, survivors from the earliest days of our world. They demonstrate that materials can endure for unimaginable spans, that information from the distant past can be preserved in the right substances, and that even the smallest objects can tell the biggest stories. And while zircons preserve information in their structure, there are structures in rock that preserve moments of ancient violence. Impact craters are scars left by asteroids or comets striking our planet. Meteor Crater in Arizona is one of the best preserved examples. Formed about 50,000 years ago, it's nearly a mile across and 570 feet deep. The forces involved are difficult to comprehend. Studying these craters helps scientists understand impact mechanics, predicting what would happen if a similar event occurred today. Larger impacts have occurred. The Chicxulub crater in Mexico, buried under sediment, but detectable through geophysical surveys, is over 100 miles wide. Even larger impacts occurred earlier in planetary history, during the heavy bombardment period, when the inner solar system was still being cleared of debris. Not all impacts are destructive in the long term. Craters become lakes, providing habitat. So impact craters are reminders that our world exists in a shooting gallery, that space contains objects that occasionally intersect our orbit, and that, when they do, the results can be catastrophic. And while impacts leave their marks from above, there are forces below, creating their own dramatic landscapes. Mud volcanoes are vents where gas and liquids from deep underground force their way to the surface, bringing mud with them. Some are small, just bubbling pools of mud. Others are large, building cones dozens of feet tall from accumulated dried mud. Azerbaijan has hundreds of them, more than anywhere else on our world. The mud contains minerals and sometimes oil, making it valuable in some cultures for medicinal or cosmetic purposes. People bathe in it, believing it has healing properties. The largest mud volcano on land is Lusi in Indonesia, created by drilling operations in 2006. This example shows that mud volcanoes can be hazards, particularly when human activities disturb subsurface pressures. Submarine mud volcanoes also exist, forming on the ocean floor, creating features affecting marine life, and sometimes producing methane seeps, supporting unique ecosystems. These underwater vents are less studied than terrestrial ones, but they appear to be common in certain geological settings. So mud volcanoes are reminders that volcanic activity isn't always hot, that eruptions can involve cold materials, and that pressure from below finds ways to reach the surface, whether through molten rock or through mud and gas forced upward by geological forces operating in the depths. And while mud volcanoes bring materials up from below, there are places where surface water disappears into Earth in spectacular fashion. Whirlpools are rotating masses of water, formed when currents encounter obstacles, causing the flow to spiral. The maelstrom off the coast of Norway is perhaps the most famous. Strong tidal currents flowing through channels between islands create powerful whirlpools that have been feared by sailors for centuries. Another significant whirlpool is Old Sow, located between New Brunswick and Maine. These features are predictable, forming when tidal conditions are right and disappearing when currents weaken. Whirlpools form because water has momentum and viscosity. When forced to change direction quickly, it doesn't turn uniformly. They're visible from above as spiraling patterns on the water surface, often with a depressed center. Smaller whirlpools form in rivers, behind obstacles, wherever water flow creates the right conditions for rotation. These are curiosities rather than dangers, interesting to watch, but easily avoided. So whirlpools demonstrate fluid dynamics visibly, showing how currents, obstacles, and tidal forces create rotation. And while water spirals above, there are spirals in stone that tell their own stories. Spiraling stones are rare geological features where rocks have been twisted into corkscrew patterns by tectonic forces. They're found in mountain ranges where ancient continental collisions compressed and folded rock. The pressure was so intense that solid rock behaved almost like putty, slowly flowing, twisting, creating shapes that seem impossible for stone. Studying these features helps geologists understand mountain building processes. The formations are visually striking, attracting photographers and geologists alike. Seeing rock twisted like a rope challenges our conception of stone as rigid and unchanging. These patterns are frozen in time, preserved when the rock cooled and solidified after mountain building ended. Not all twisted rocks form spirals, so spiraling stones are geological sculptures, art created by tectonic forces acting over millions of years. They remind us that our planet's history is written in rock, that landscapes we see today were shaped by processes operating at scales difficult to imagine, and that even stone, given the right conditions, can twist and flow like water. And while stone can spiral under pressure, there are creatures that spiral through water in pursuit of prey. Dolphins hunt using bubbles, creating nets of air that trap fish. This behavior, called bubble net feeding, requires coordination. Multiple dolphins work together, timing their swimming to maintain the bubble wall, while others position themselves to drive fish toward the center. Humpback whales also use this technique, though on a larger scale. Watching this from above, perhaps from a boat or aircraft, is spectacular. Not all dolphins use this method. It seems to be specific to certain populations, suggesting it's cultural rather than instinctive. The technique is effective, but energy intensive. Research into these behaviors provides insights into animal intelligence, cooperation, and culture. It shows that dolphins and whales are not just reacting instinctively, but thinking, planning, and using tools, in this case, bubbles, to achieve their goals. So bubble net feeding is an example of sophisticated behavior in marine mammals, evidence of intelligence, cooperation, and culture in species very different from us. And while dolphins create temporary structures to catch food, there are animals that build permanent structures, reshaping coastlines. Oyster reefs are built by oysters attaching to hard surfaces and to each other, creating complex three-dimensional structures that can extend for miles along coastlines. A single adult oyster can filter up to 50 gallons of water per day, removing algae, particles, and pollutants. A healthy reef containing millions of oysters can filter the entire water column of an estuary multiple times per week, dramatically improving water quality. The physical structure provides habitat. They also protect coastlines. The rough, complex surface of reefs breaks waves, reducing energy before it reaches shore. But oyster populations have declined dramatically. Restoration efforts are underway in many places. The process requires patience and continued effort, but results are encouraging. Restored reefs begin filtering water within months, attracting other species within seasons and providing measurable benefits within just a few years. So oyster reefs are foundation species, organisms creating habitat and conditions allowing many other species to thrive. And while oysters build reefs from their shells, there are organisms building structures from materials they secrete. Termite mounds are engineering marvels, structures built by millions of tiny insects working without central coordination. Some mounds rise over 20 feet tall, constructed from soil mixed with saliva and feces, creating material hard as concrete. The mounds are climate controlled. The principles are so effective that architects study them, applying similar concepts to human buildings. Inside the mound, termites maintain fungus gardens, feeding them chewed plant material and harvesting the fungus to feed the colony. It's a form of agriculture, cultivating food rather than hunting or foraging. The queen lives in a central chamber, protected by walls and surrounded by workers and soldiers. Termite mounds affect landscapes. In savannas, they create patterns visible from space, regularly spaced mounds dotting the terrain. Some mounds are ancient, inhabited continuously for centuries. So, termite mounds are monuments to collective effort, demonstrations of what can be achieved through cooperation and specialized roles. And while termites build up, creating structures above ground, there are final connections we must consider in how life, water, and stone weave together across our world. The water cycle connects everything. Every drop of rain that falls has been somewhere else before. Part of the ocean, part of a river, locked in ice, inside a plant or animal. Some water completes the cycle quickly. Still other water is stored for ages. Glaciers hold water that fell as snow thousands of years ago, slowly compacting into ice, holding onto it until warming eventually releases it. The cycle is powered by the sun, which provides energy for evaporation, and the amount is constant. This cycle is also how pollutants spread. Chemicals washing into rivers don't disappear. Climate change is altering the cycle. Understanding the water cycle is important for managing resources. Where water comes from, where it goes, how long it takes, how much is available. All these questions are relevant for agriculture, for cities, for ecosystems, and there's beauty in the concept. So, the water cycle is the ultimate connector, moving water through every part of our world, linking mountains to oceans, clouds to trees, humans to all other life. And so, here we are, 100 facts about our planet. Tomorrow, when you wake, the sun will rise on the same world, but perhaps you'll see it differently. Perhaps you'll remember that nothing here is ordinary. The water will still flow. The wind will still blow. Sleep now. Let these wonders settle into your dreams. Let the knowledge of your connection to all things, to all time, to all the patient processes shaping this world, carry you gently into rest. You are made of star stuff, organized by happenstance into consciousness, alive on a planet spinning through darkness, warmed by a nearby star, protected by invisible fields, surrounded by neighbors who share your air and water, and the remarkable fortune of existing here, now, in this moment. And that is enough. Rest well. The world will still be here in the morning, still turning, still beautiful, still full of wonders we've barely begun to discover. And you'll be here too, part of it all, connected to everything, as you've always been, as you'll always be. Good night.